In this final video, we are going to cover two more advanced topics when looking at a graph, which would be computing betweenness centralities of vertices and also computing the Cheegar constant of the graph. So let's start with betweenness centralities. And generally speaking, to get an idea of what you're trying to measure with betweenness centralities, I want to go back to this idea of thinking of the vertices as landmarks and the edges as paths that you can walk between those landmarks. And what you're really trying to measure with a betweenness centrality is how important that vertex or that place is in terms of traveling from one point to another. And so thinking about what vertex is a cut point or not is one way of measuring that importance for the dissemination of information. Betweenness centralities are going to try to capture a little bit more of how important the number is, not just whether or not it's a cut point, but just how much it's contributing overall to the passage of information or resources. So let's walk through this one at a time. Betweenness centralities have a somewhat difficult definition that I provided for you in the worksheet, but what we're going to be doing is computing the betweenness centrality, for example, of the vertex 2, and in the end what we're going to do is take a big long sum of a whole bunch of terms, much like when we were computing powers of a matrix, but what we'll be doing is looking at all possible pairings of vertices, ignoring the vertex 2. Since we're computing the betweenness centrality of vertex 2, 2 is excluded from this computation, and what we're going to be doing is computing the number of geodesics between those 2 points, and that value is going to go right here. And then by n sub xy with this superscript 2, we'll be saying, and how many of those geodesics involve this special number that we're computing the betweenness centrality of, so in this example 2. So we'll be counting how many shortest paths there are between 2 vertices, and then how essential is 2 in looking at those shortest paths. So for example, with 1 and 3 here, we have 2 different geodesics. We have the geodesic ED and the geodesic AB, as we saw previously. 2 total geodesics, one of which involves the vertex 2. And so we look at that ratio of those that involve 2 to overall total number of geodesics, and that becomes the summand from the 1-3 part of this comparison. And we've got to keep going, looking at examples like 1 and 4. We find that there are 2 geodesics between 1 and 4, this path EDC and this other path ABC, and that path ABC does involve the vertex 1, so overall we'll get another 1/2 contributing to this total sum. Now something different happens when we look at vertices 1 and 5 paired up, which is that there's really only one geodesic between them. That's the edge E, and none of those geodesics involve the vertex 2. And so we don't get anything being contributed to the sum here, as 2 is totally unimportant in terms of the passage of information between vertices 1 and 5. And in fact, we get really lucky with this graph because that's the case for the remainder of the pairs of vertices. 2 is not important in the passing of information between 3 and 4, nor is it important from 3 to 5 or 4 to 5. So altogether, a whole lot of zeros, but what we do is we compute the total betweenness centrality of 2 by adding everything that occurred in that bottom row of the previous table, 1/2 plus 1/2 plus a whole bunch of zeros, and we get this value of 1. So the last thing I want to stress to you about betweenness centralities is that it's not 1 that's special about the number 2. At most, we could have a vertex that appears in every single path of every single possible geodesic. That would be a super important point in a graph. And so at most, your betweenness centrality will be equal to the number of vertices that you have minus 1. However, your betweenness centrality could be 0 if you have a point that's just absolutely unimportant for the passage of information. And so there's a wide range of values that can occur for the betweenness centrality of vertices. So if you really want to know which is the most important vertex in your graph, you're going to have to compute the betweenness centralities of all vertices and compare their relative size. The last thing we're going to take a look at here is the Cheegar constant of a graph. So again, similar to betweenness centralities, there are a lot of computations that need to be computed in order for us to determine the Cheegar constant. What we'll be doing is taking a look at all different possible subsets of vertices that contain at most number of vertices over 2 elements. What we'll really be doing is sort of splitting the vertices in half, and we're going to just focus on the sets that are the smaller of those halves. So we'll be dividing the vertices into the subset that we're looking at and then an everything else subset, which is the complement of that. And we'll be then looking at the boundary of that set, or what is called the boundary of that set, and is denoted with this partial derivative symbol. And we'll be saying what that boundary is. It's the collection of edges that contain an element of the set that we're deeming A, and also an element of the complement of that. So the number of edges with one thing in the set A and one thing out of the set A. For our example, we have 5 vertices, so we need to look at all possible subsets of size 1 and then all possible subsets of size 2, and we'll compute all of these different ratios of boundary edges to size of the set, and then we'll find the minimum element of that set for the Cheegar constant. But something nice happens when we're looking at single vertices in this example. So I've highlighted 2 just to give us some concrete structure, but when we pick a single vertex, every single edge that contains that vertex is going to be considered a boundary edge because we only have the one element in the set. Everything belongs to the complement, and so every single edge is an edge that belongs to the boundary. So what we're going to get in that formula of the ratio of the size of the boundary to the size of the set is just the degree of that vertex. And that doesn't really matter about the 2. So we're going to be looking at one collection, one part of the set that we'll be taking the minimum over is going to be the degrees of the vertices in the graph. For pairs of vertices, we're going to have to do something similar to what we did with the cut points, where we look at all possible pairs of vertices and just identify what that boundary is. And what the contribution is going to be overall to this set, which is that ratio, the size of the boundary to the size of the set. So starting with 1 and 2, we have a total of 1, 2, 3, 4 edges. However, the edge A, which is between vertex 1 and vertex 2, if 1, 2 is our set A, then this edge only consists of elements in A, and so it's not something we want to count as part of the boundary of that set. Just these edges, E, F, and B, belong to the boundary because they represent edges with one vertex that's in the set A and one vertex that's outside of that set. When we then divide that by 2, the number of elements in the set A, we get a total contribution of 1.5. And I've walked through the rest of these step by step. Vertices 1 and 3, they actually don't share an edge at all, and so every single edge that's involving either 1 or 3 is going to belong to that boundary. We divide by 2 for a contribution. A similar thing happens with 1 and 4. There just happen to be fewer edges, so every one of those 3 edges belongs to the boundary. And then that pattern continues in how I've highlighted things. I've highlighted edges in blue if they are edges containing the 2 vertices, but they do not belong to the boundary. And in red, I've highlighted the edges that we do want to count as part of the boundary of those 2 vertices. And I've then divided all of those things by 2 in order to determine the contribution. As we walk down this list, you'll find that 3, 4 here actually gives us the smallest contribution of all possible pairs because we have 3 total edges. One of those edges belongs to the boundary. One of those edges does not belong to the boundary because it's between the 2 elements of the set, and so the 2 remaining edges belong to the boundary. There are 2 things in the set, so we get this total contribution of 1. And you can start to ask yourself some questions about when am I going to get a really small contribution to this collection of ratios. And what you're looking for is a collection of vertices where there aren't that many edges reaching outside of that set. There might be a lot of edges within that set, there might not be, I don't know, but there aren't that many edges extending from the set you're looking at outward. And so that's what your Cheegar constant is really trying to measure. is what's the sort of worst case scenario we could have with that, or best case scenario, depending on your perspective. We finish up with 3, 5, and 4, 5, but it's much of the same. So altogether, to compute that Cheegar constant, we'd be looking at the minimum of the first set that we have here. It's coming from the degrees of the vertices. And then we take the union with the set of values that occurred in the table that we computed previously, 1.5, 2.5, 2, and 1. And either way, either coming from the degrees or coming from that 3, 4 combination over here, the smallest value that we see is 1. So that's the Cheegar constant of our graph.